So now we're going to talk about two lessons, lessons 20 and lessons 25. So lesson 20 is about the ratio and root tests for a convergence of series. So we're interested in infinite series, summation a sub n, say from 1 to infinity. What does it mean for a series to converge? It converges if the sequence of nth partial sums. The nth partial sum is the sum of the first n terms of the sequence. If this sequence of numbers converges, the sum limit L as n goes to infinity. And in that case, we say summation an, n goes from 1 to infinity, converges to L. Now, an can be positive or negative, and we also say something much stronger, that the series summation an, n goes 1 to infinity, converges absolutely if the sum of the absolute values of these numbers converges. And because an is always between the absolute value of n and minus the absolute value of n, absolute convergence of a series implies convergence. That is, if a series converges absolutely, then it converges by the comparison test. Now, there are two very useful sufficient conditions for absolute convergence of a series. And the first is what is called the ratio test. So summation an, n goes from 1 to infinity, converges absolutely if you take the limit of the ratio of successive terms, this limit exists and it's a number less than 1. Summation an diverges if the ratio of the absolute values of successive terms converges to a number bigger than 1 or infinity, and we have no information if the limit is equal to 1. Or if the limit doesn't exist, let's say. I mean, the idea of the proof is very simple. Recall the geometric series. Summation r to the n goes from, let's say, from 0 to infinity, converges to 1 over 1 minus r if the absolute value of r is less than 1, and it diverges if the absolute value of r is greater than 1. So let's suppose that the limit of an plus 1 over an is some number r less than 1 as n goes to infinity. So, or let's just put it like this, is less than r. This means that less than 1. The limit is less than 1. This means that there exists an n such that an plus 1 over an, an absolute value, there exists an n, and an r strictly between 0 and 1, such that an plus 1 over an is less than or equal to r for all n greater than or equal to n. So if an plus 1 over an is less than or equal to r for n greater than or equal to n, then what does that mean? So it means that an plus 1 is less than or equal to absolute value of an times r. And an plus 2 is less than or equal to an plus 1 times r. So let me just say, so I'm going to use then that for every n, an plus 1 is less than or equal to an times r for n greater than or equal to n. So an plus 2 is less than an plus 1 times r, but an plus 1 is less than an times r, makes that r squared. And an plus 3 less than or equal to an plus 2 times r is less than or equal to an r cubed. And in general, an plus k is going to be less than or equal to an r to the k and greater than or equal to 0. So by comparison with the geometric series, summation an converges absolutely. If the ratio of an plus 1 over an converges to something greater than 1, then we're going to have an plus k greater than an plus k minus 1. These terms are going to get bigger and bigger and bigger. They're not going to go to 0, and the series diverges. I mean, this has to be written down in more detail, but that's going to be the idea. What about the root test? Well, sorry. What would be an example? Suppose we take summation 2 to the n over n factorial as n goes from 1 to infinity. Can we show the convergence or divergence of this series? Well, what's the ratio of successive terms? So an is 2 to the n over n factorial. An plus 1 is 2 to the n plus 1 over n plus 1 factorial. So if I look at the ratio an plus 1 over an, that's n plus 1 factorial over 2 to the n plus 1. And 1 over n is 1 over an is n factorial over 2 to the n. Oops, sorry, is an plus 1, let's write this correctly, is 2 to the n plus 1 over n plus 1 factorial. This is 2 over n plus 1. And this goes to 0 as n goes to infinity. So by the ratio test, the limit is 0, which is less than 1. So this series converges. What is the root test? So the root test says that if you have this infinite series, this converges if you take the nth root of the absolute value of an. If the limit of this as n goes to infinity is less than 1, it converges. And the infinite series an converges, in fact, absolutely. And the infinite series diverges if the limit then goes to infinity, nth root of the absolute value of a sub n is greater than 1. If it's equal to 1, we have no information. So here's an example. Summation e to the power 2n over n to the n. So a sub n is e to the 2n over n to the n, which is e squared over n to the nth. So the absolute value of a sub n is, and then the nth root of the absolute value of a sub n is the nth root of e squared over n to the n, which is e squared over n. So if we take the limit as n goes to infinity, that's 0, which is less than 1. So the series converges. And the important application to Taylor series is the following. Recall a Taylor series is of the form, well, an example would be summation a sub n x to the n. Then goes from 0 to infinity. So the nth term is an x to the n. So in the ratio test, we would be looking at an plus 1 over an, which is an plus 1 x to the n plus 1 over an x to the n, which is an plus 1 over an, absolute value of x. And we take the limit as n goes to infinity. And if this ratio has a limit, we get some interval of x's where the series will converge. If we take this series summation an x to the n and apply the root test, we're looking at the nth root of the absolute value of an x to the n, which is the nth root of the absolute value of x, absolute value of a sub n, times x. And again, we ask about the limit of this as n goes to infinity. So this connects us to lesson 25, which is Taylor series. So the idea is to approximate an arbitrary function by a Taylor polynomial and of degree n, but if you let n go to infinity, you get an infinite series. And the question is always, does this infinite series equal the function on some interval. Not necessarily everywhere, it could be everywhere, but not necessarily everywhere. So given a function f of x and a point C on the real line, we have the Taylor series for f of x. It's an infinite series, a0, sorry, not a0. The constant term is f of 0 plus, let's say f of c, plus f prime at c, x minus c, plus the second derivative at c over 2, x minus c squared. In general, this is an infinite series. Summation n goes from 0 to infinity. The nth derivative of the function at c over n factorial, x minus c to the nth. We'll just recall that the 0th derivative of a function at c is just the value of the function, and 0 factorial is defined to be 1. At c equals 0, the Taylor series is also called the Maclaurin series. And the series looks like summation nth derivative at 0 over n factorial, x to the n, c is 0, so x minus 0 to the n is just x to the n. And the question is, does this series converge to f of x on some interval centered at c? So here's the point c, which could be 0, and then maybe c plus r, c minus r. In some interval centered at c, does the series converge, and does what it converges to actually equal the function? So that is always the question. So let's start by computing some examples. Let's say I want to compute the Taylor series for f of x equals the cosine of x centered around 0. So I need to know all the derivatives of the function and their values at 0. So we have f of x is the cosine, f prime of x is minus the sine, second derivative is minus the cosine, third derivative is, let's see, cosine minus sine minus the cosine. The derivative of minus the cosine is plus the sine. And the fourth derivative is the cosine. So it repeats. And then it's going to keep repeating forever. Cosine minus sine minus cosine sine. Cosine minus sine minus cosine sine. What are the values at 0? Cosine of 0 is 1. Sine of 0 is 0. Minus the cosine of 0 is minus 1. Sine of 0 is 0. Fourth derivative at 0 again will be 1. So in general, what we have is that f to the n of 0 takes on 1 if n is a multiple of 4, minus 1 if n is 4k plus 2, and 0 if n is odd. So the Taylor series for the cosine looks like, so it's summation f to the n of 0 over n factorial x to the n. and goes from 0 to infinity. But of course, if n is odd, the derivative is 0. So we only have to go through even numbers. And the even numbers will oscillate 1 minus 1, 1 minus 1. So you get 1 minus, so what do we get when k is equal to 2? 1 over 2 factorial x squared. When k is equal to 4, 1 over 4 factorial x to the 4th, minus 1 over 6 factorial x to the 6th, plus 1 over 8 factorial x to the 8th, and so on forever. That is the Taylor series. Let's look at another example. Suppose I take sine squared. So what are the derivatives? This gets more complicated. So that's f of x. F prime of x is 2 sine x cosine x. F at 0 is 0. F prime of 0 is 0. What is the second derivative? When I differentiate this, I get 2 cosine squared x minus 2 sine squared x. The second derivative at 0 is 2. What is the third derivative? I differentiate this. I get 2 times the derivative of cosine squared. That's 2 cosine x times minus sine x, minus 2 times the derivative of sine squared, which is 2 sine x cosine x. So I have minus 4, I have minus 8 cosine x sine x, and the third derivative at 0 is 0. More complicated than I might have thought. What's the fourth derivative? The fourth derivative of this is 8 sine squared x minus 8 cosine squared x. So the fourth derivative at 0 is minus 8. So if we want to write down the first 4 terms in the Taylor expansion for sine squared, we would have f of x equals, the constant term is 0, plus 0 times x, plus 2 over 2 factorial x squared, plus 0 over 3 factorial x cubed, plus minus 8 over 4 factorial x to the 4th. So this is 1/2 x squared minus 1/3 x to the 4th, and so on. Let's just stop right there and see if we can find a better way to work this out. So we had that the Taylor series for sine squared x starts with 1/2 x squared minus 1/3 x to the 4th, and so on. Let's figure out a better way perhaps to do this. So we remember sine squared x is one plus cosine 2x over 2. Right? Why is that? Remember, cosine 2x is cosine squared x minus sine squared x. Cosine squared x is 1 minus sine squared x minus sine squared x is 1 minus 2 sine squared x. So 2 sine squared x is 1 plus cosine 2x. So if we divide by 2, we get this formula. Now, we know what the cosine is, don't we? Cosine of x is 1 minus x squared over 2 plus x to the 4th over 4 factorial minus x to the 6th over 6 factorial and so forth. So the cosine of 2x is 1 minus 2x squared over 2 plus 2x to the 4th over 4 minus 2x to the 6th over 6 factorial. Sorry. Yeah, that's right, over 6 factorial. This is 2 factorial, 4 factorial. So 1 plus the cosine of 2x is equal to 2x squared over 2 factorial plus 2x to the 4th over 4 factorial, sorry, minus, I'm just rearranging this, plus 2x to the 6th over 6 factorial and so forth. So this is equal to 4x squared over 2 minus 16x squared, 4 factorial is 24, 2 to the 6th is 64x to the 6th over 6 factorial is 720, I believe. And if I divide by 2, what do I get? I get x squared minus 16 minus x to the 4th over 3 plus, let's see, 720 is, so I have 64 over 2 times 720. That's 32 over 2. Divide by 4, this is 8. Divide this by 4, I get 180. Divide it by 4 again, I get 4 into this is 445. 2 over 45 x to the 6th. The only thing that bothers me is I should have a 2 here. So let me just double check. Cosine x is 1 minus x squared over 2. So if I replace x by 2x, I get 2x squared or 4x squared over 2. So this is 4x squared over 2. And I divide by 2. Let's see, why is this not working out properly? Let me just check what I did when I started to calculate the Taylor series for sine squared of x directly. The second derivative was equal to 2. So 2 over 2 is 1. So this should just be x squared minus 1/3 x to the 4th. Good. So this is x squared minus 1/3 x to the 4th. But I had a sneakier way of doing it. I could just use the fact that I had the Taylor series for cosine x, replace it with x with 2x, and I already get the first two terms plus one more term very easily. That's not bad. Let me go back one more time to this Taylor series we got for the cosine of x. We had calculated this in a previous lecture. So we have the series cosine x equals summation, I'll write it a sub n, x to the n, well, sorry, a sub n, and goes from 0 to 2n, where the nth term is equal to x to the 2n over 2n factorial minus 1 to the n. So if we look at the ratio of successive terms, an plus 1 over an in absolute value, I get x to the 2 times n plus 1 over 2n plus 1 factorial, 2n factorial over x to the 2n. This is equal to x squared over two n plus 1 times 2n plus 2. And this goes to 0 as n goes to infinity for all x. So therefore, the Taylor series where cosine x converges for all x. That's the point. Let's compute another Taylor series. One of the things to learn is simply the skill, the technical ability to compute a Taylor series. Suppose we take f of x equal the square root of 1 plus x. Of course, this is only defined for x, for 1 plus x greater than or equal to 0, or x greater than or equal to minus 1. If x were less than negative 1, this would be a negative number. So we're not going to get a series that converges for all x. But what is the derivative? The derivative of 1 plus x to the 1/2 is 1/2 1 plus x to the minus 1/2. The second derivative is 1/2 minus 1/2 1 plus x to the minus 3/2. The third derivative is 1/2 minus 1/2 minus 3/2 1 plus x to the minus 5/2. The fourth derivative is 1/2 minus 1/2 minus 3/2 minus 5/2 1 plus x to the minus 5/2. This is fun. The fifth derivative is 1/2 minus 1/2 minus 3/2 minus 5/2 minus 7/2 1 plus x to the minus 7/2. Let's see. This is equal to minus 1 over 2 squared, 1 plus x to the minus 3/2. This is plus 1 or minus 1 squared, 1 times 3 over 2 cubed, 1 plus x to the minus 5/2. Minus, 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 this is minus 1 cubed, 1 times 3 times 5 over 2 to the 4th, 1 plus x to the minus 5 halves. Here I have 4 minus signs, minus 1 to the 4th over 2 to the 5th, 1 times 3 times 5 times 7, 1 plus x to the minus 7 halves. If you wanted to make a nice guess, you would say the nth derivative of x was equal to minus 1 to the n minus 1, 2 to the n, and the product of the first n minus 1 odd numbers times 1 plus x to the minus n plus 2 over 2. So the zeroth, so the value of this when x equals 0, this just becomes 1. It's minus 1 to the n minus 1, 1 times 3 times 5 up to 2n minus 1 over 2 to the n. So we get that the Taylor series for the square root of 1 plus x is what? Well, when x is 0, it's 1, plus the derivative at 0 is a half. And now it starts to oscillate in sign, positive, negative, minus 1 over 2 squared x squared, plus 1 times 3 over 2 cubed x cubed, minus 1 times 3 times 5 over 2 to the 4th x to the 4th, plus 1 times 3 times 5 times 7 over 2 to the 5th x to the 5th, and so forth. Yeah. You get a series that looks something like that. Well, there are a lot of examples in the text and in the homework problems, and I'll do a number of them in the problem sessions.